Welcome back to Static and Current Electricity, Magnetism and Transformers. And we're going to move right along into magnetic energy. Magnetism is a force that attracts certain materials such as iron, nickel, and cobalt. So to remember this, I would always tell students to remember the acronym NIC, N-I-C, N for nickel, I for iron, and C for cobalt. A magnetic field is a space around a magnet where its magnetic effects can be felt. And here we have the magnetic field lines, and as you can see, the field lines always go from north to south. Okay, the direction of the arrow is always from north to south. Okay, please note that north unlike poles always attract and like poles repel. Okay, if you had the south pole here, you would have something like this. Instead of the arrows going away from, if you had the south pole, the arrows would be going away from, but the arrows would be going, so basically the lines, there's repulsion, sorry, but the arrows will be coming towards the south pole. Okay, all right. Now the earth is a large but weak magnet. If a bar magnet is freely suspended, it aligns itself in the direction of the earth's magnetic field. The north pole of earth should be referred to as the north-seeking pole, since it is actually a south pole attracting the north pole of the magnet in a compass. Likewise, for what is referred to as the south pole of earth. So we see here that what we call north is actually south, and what we call south is actually north. And what is actually happening is that the north pole of the magnet in the compass is attracted to the south pole, the geographical, the real south pole. But we call this the geographical north pole, because the north pole of the magnet is attracted to the actual south pole, right? And then you have the south pole of the magnet being attracted to the actual north pole. Okay, I know you're probably going like, huh? Yeah. So the south pole of the earth should be referred to as the south-seeking pole, since it is actually a north pole attracting the south pole of the magnet in a compass. The poles on a magnet are the areas where its magnetic strength is strongest. A magnet is dipolar, which means that it has two poles, the north and the south. The laws of magnetism are: like poles repel and unlike poles attract. A magnetic material is a material which is attracted to a magnet or which can be magnetized. Nickel, iron, and cobalt are the only naturally occurring magnetic materials. Other magnetic materials are alloys such as steel, which is a mixture of iron and carbon. Magnets come in a variety of shapes and sizes, like the bar, the horseshoe, U-shaped, and ring. And I have some pictures here so you can see, and some of you might have seen these already. There are two types of magnets. You have permanent and temporary magnets. Steel is a permanent magnet. Iron is a temporary magnet. Iron and no metal are classed as soft magnetic materials and are used to make temporary magnets. They are easy to magnetize but do not retain magnetism well. Steel is classed as a hard magnetic material. It is more difficult to magnetize, but it will retain its magnetism for longer. It is used to make permanent magnets. Magnetized magnets are also permanent. So here we're going to compare permanent magnets with temporary magnets. A permanent magnet will remain magnetized even after the cause of magnetizing is continued, whereas a temporary magnet loses its magnetic properties when the cause of magnetizing is discontinued. In permanent magnets, the strength is constant, whereas in temporary magnets, its strength is varied. Permanent magnets are steel And with temporary magnets, you use iron. Places that permanent magnets are used: clasps for jewelry, compasses, credit cards, doors of refrigerators and dishwashers, ornamental articles attached to those that are attached to refrigerators. And with temporary magnets, they're using cranes, electric guitars, doorbells, microphones, generators. In industry to lift steel, in industry to lift iron and steel, road and sheets. Let's in industry to lift iron and steel rods and sheets, motors, loudspeakers, medicine for MRI, such as magnetic resonance imaging, telephones, televisions, and computer monitors. Magnetism may be induced in some metals by a process called induction. Magnetic induction is the process by which magnetic properties are transferred from one body to another without physical contact. Induction may involve stroking, which is a form of rubbing, or application of a current to a metal. So here we have two examples of stroking. You have single stroking, and this is using a metal on top, using a magnet rubbing a metal, and double stroking using two magnets rubbing a metal. And as you can see, for one end to produce the south pole, you use the north and go this way, and the south pole to produce a north pole, you use the south pole side to rub in anti-clockwise motion. So you will see, in clockwise motion. So to get a north pole, you go in clockwise motion, and to get the south pole, you go in anti-clockwise motion by rubbing the north pole along the metal strip. And you can see it right here. And then to induce a current instead of something that would not have been magnetic but does have magnetic properties, you would run a piece of wire, you wrap it around like a nail and run some electricity inside of it. Why can this happen? Well, magnets contain domains, or things called dipoles. In magnetized metals, the domains or dipoles are aligned. Okay. However, in metals that are unmagnetized, the tiny magnets referred to as domains or dipoles are not aligned. Inducing magnetism in unmagnetized metals causes domains to align, making the metal become magnetic. An electromagnet is made by passing an electric current through a coil of wire. And now the strength of an electromagnet is increased by 1, increasing the amount of current being passed through the coil, 2, increasing the amount of turns of the coil around it, and 3, by using a magnetic core instead of the coil. Now it says, how would you test a metal to determine if it is a permanent magnet? A permanent magnet causes repulsion with the one pole when both poles are in turn brought near to a suspended magnet. So that's a sure way, the repulsion test. An unmagnetized magnet material will give attraction with both poles, and that would be suspect for it being unmagnetized or not being permanent, right? Why are electromagnets more commonly used than permanent magnets? That's because you can control them. You can also, in terms of control, means that you can turn it off or turn it on, 1. 2, you could actually increase the strength or decrease the strength. So this is all falling under control, right? How may electromagnets be made stronger? You can increase the number of coils around the metal. You can also increase the current being passed through the metal, or you can add a very strong magnet. What are where are electromagnets used? I'm going to give 2. So 1, fire alarms, 2, doorbells. Current and magnetic fields. So this one you have to pay special attention to. Okay? The charges moving in a wire produce a magnetic field around that wire. Current can be made to pass perpendicularly through a sheet of horizontal card or paper. Using iron filings or the compass method, they will show that there is a circular path or field around the wire. To determine which way the field lines loop, you can use the right hand grip rule. So this is my right hand, okay? So I'm going to tell you now, use a pen, and it says grip the wire with the right hand. The thumb is placed in the direction of the current. So once you know the direction of the current, you can just wrap your hand around it using your thumb. So basically, if the current in my pen is going to the north, then I would just keep my thumb up and just put the pen in between my fingers. Looking at the direction that your fingernail is going, you could decide the direction of the magnetic field lines, and in this case it's going anti-clockwise. If you keep going around, you will see it's going anti-clockwise, right? Now, if the current is going down this way, right, you will see the field lines are going clockwise. If you do your finger around, going in the direction of your fingernails, you will see it's going clockwise. The magnetic field around a single wire is not strong, and so coils of wire called solenoids are used to make them stronger. One end of the coil acts as a north pole and the other acts as the south pole. To find the direction of the field from the direction of the current, we can use our right hand again. Your fingers follow the direction of the wire curving around the coil. Your thumb will point in the direction of the magnetic field, which is northwards. So to give you the arrows right there, you can just follow. So your fingers would follow the arrows, right? And wherever your thumb pointing, that's where north is. So if you look in the other picture, you will see it's just the opposite direction, and you see north will be flipped the other way if your hand is going down, right? The strength of a magnetic field produced by a solenoid may be increased by using more loops or turns of the wire, increasing the current of the wire, or placing an iron core inside the solenoid. This has the effect of concentrating the field lines, creating a strong field at the end of the core. Powerful electromagnets can be produced by using all of these measures. So an electromagnet, as we learned earlier, can be made by wrapping a wire multiple times around a nail, which is connected to a power source. Once that circuit is closed, then the iron nail should act as a great magnet. It would just start picking up stuff, right? So you could try that at home. When an electric current, so the working of an electromagnetic field. So when an electric current runs through a wire, an electromagnetic field is generated around it, like what we were doing with the right hand grip rule. Now if you take that wire and make it into a coil, the same way you see in the first picture, you make it into a coil, this makes the magnetic field stronger, right? So it says by winding the wire into a tighter coil, the field is made stronger, that is higher current, and more numbers of wire turns produce a stronger field. Okay? The field can be made stronger by placing an iron bar in the coil center, thus increasing the power of the electromagnet. And that's what we've been saying. This is the third time we've said this, right? Things that make electromagnets stronger. So when a wire carries a current, there will be a magnetic field surrounding that wire. So they work together. If the wire is placed inside the magnetic field produced by a permanent magnet, then the two magnetic fields, the one that was already there and the one that's existing between the magnet now, will interact with each other. And this will cause a force to act on the wire and the permanent magnet. This will happen provided that the wires are not placed parallel to the magnetic field lines. So that means it's cutting the field lines, and this is called the motor effect. The size of the force acting on the wire will depend on the following. The current, so these are what affects the strength of the magnetic field, and this is the fourth time it's being said again. The current in the wire, the larger the current, the stronger the magnetic field, the strength of the magnetic field from the permanent magnets, and 3, the length of the wire inside the permanent magnet's field. The force will be greater the longer the wire. So this is similar to the electromagnet, right? So it's not really the same, but similar. So using Fleming's left hand rule, so this is our left hand, it can be difficult to work out the direction of the force acting on the wire in a magnetic field. Fleming's left hand rule, also known as the motor rule, lets us find the direction of the force acting on the wire when we know the direction of the current and the magnetic field. So pretty much you just need to know what the thumb, your index finger and your middle finger stand for. So your thumb is for movement. So if you have a pen next to you, you can write where your thumb is. So you put M on your thumb. Movement. Your index finger, which I call the first finger, represents the magnetic field lines. So you just put F for magnetic field lines. And then the second finger represents the current, the direction of the current, so you could put C. So just like how I have these here, you can write them down, right? And then you can put all your fingers at 90-degree angles to each other. So your thumb will be at 90 degrees to your first finger, and this one will be 90 degrees to your first finger as well. So all of them at 90 degrees. So it looks like this way, it looks like this way, and this way, right? Now, it says the magnetic field direction is from north to south, so we have to remember that. So if you have a magnetic field that's north here and south here, you put your fingers like this. You put your field line finger in that direction, right? And if that's the case, if the magnetic field was north here and south here, right, and the current was coming to me, then the motion of the wire will be going up, right? Now if I turned it this way and the field line was going north to south right there, so your finger is that way and the current is going to you, then the direction of the wire that's going to be affected will be down. Okay, and this is important in knowing how to learn the left hand rule for the motor, to know how the wire is going to turn, because that's what the question is always about, the motion of the wire. Right, so using Fleming's left hand rule, answer the following question. It says, the figure below shows a current carrying wire. A magnetic field is acting into the paper. In which direction is the force acting on the wire? So in this question, the magnetic field is going into this paper. So we're going from north to south into this paper. Current is going that way. As you can see the arrow, the current is going in that direction. So therefore, if it's going into the paper and current is going that way, motion of the thumb will tell us that the wire is going to go up. Okay? The motion of the wire is going to go up. Good. Now, we're going to learn about magnetic induction, electromagnetic induction. So, if an electrical conductor cuts through magnetic field lines, a voltage is induced across the ends of the conductor. So in this case now, there is no current traveling through the wire. The wire now is cutting through the magnetic field lines, and we are attaching it to an ammeter. And remember that ammeters measure current. And what you're going to realize is that passing this wire through the magnetic field lines causes it to be cutting the magnetic field lines, and it's going to produce a current, right? So that's the electromagnetic induction right there. The current is only produced once the field lines are cut, so therefore some mechanical energy must be put. Alright, so I got cut off, the camera died, and we are back. So it says, so I was telling you that what they found was, if you took a wire and passed it through a very strong magnet to cut the field lines, current would be produced, would show that a current is going to be produced in that wire, as shown on the ammeter, right? However, the only thing is that mechanical energy was needed for this. Somebody or something had to keep moving the wire up and down through the magnets, okay? And this is called electromagnetic induction, and is sometimes referred to as the generator effect. It is the cutting of the magnetic field lines of force by the wire, which places a force on the electrons within the wire, which causes the induced effect. Pushing the magnets or north pole first into the solenoid so that the magnetic field lines pass through the loops of wire induces a current in the wire. So this is us investigating induction. Okay, so now we have a wire. So remember before we had the wire cutting the field lines. So now we're going to have a magnet passing through the wire and the field lines being cut, right? So pulling out the magnet induces a current in the opposite direction. Okay, so if it induces a current in the opposite direction, then you're going to see that this pointer will just move on the opposite way. Reversing the direction of the magnet, pushing in the south pole will also reverse the direction of the current, right? So again, pulling out the magnet induces a current in the opposite direction, and reversing the direction of the magnet, so pushing in the south pole will also reverse the direction of the current, right? The faster the magnet is moving relative to the coil, the greater the current. So in and out, the current will be faster. This shows that it is the rate that the wire moves through the field lines that is the cause of the increased current. The more loops of wire in the solenoid, the greater the induced current. The stronger the magnet, the larger the induced current. Leaving the magnet inside the coil does not produce a current, so there must be some movement, okay, to cut the field lines. The current induced in the coil will change direction as the magnet is moved in and out of the coil, so like an alternating current. To determine the direction of the current in a solenoid as the magnet moves, the following solenoid rule is used. The current induced in a solenoid always acts in such a direction as to oppose the change that causes it. Therefore, when the north end of the magnet is pushed into the coil, that end of the coil acts as a north pole. But when the magnet is withdrawn, the magnetic field reverses. Alright, so this is the end of part 6, and I hope you did enjoy, and I hope you understood what I was teaching. Please look out for my questions. I don't think I'm going to have questions in a lump for this topic. I think I'm going to do it in parts, and I hope you do enjoy and appreciate what I am trying to do. See you around. Bye.